Hey, Dr. Clark coming back at you with an example video here. We're looking at properties of the Laplace transform worked out. And what we're going to do is a couple of examples using the translation theorems here. So the first example we've got is an initial value problem, first order. And it looks like we've got a forcing term right-hand side, but the way that forcing term looks is it's sort of it's 0 up until t equals 4 here, and then it starts looking like t for t's bigger than 4. Of course, for t's bigger than 4, t is actually equal to 4, and then going up by t. So that's kind of the look of this of the forcing term, right? And so this is going to be the kind of forcing term we should be able to handle with Laplace transform, but we're going to need to write it in terms of the unit step function. So f of t is really just t times the unit step function starting at t equals 4. So that's what the unit step function will be, because it's just going to be 0 from 0 to 4, and then starting at 4, it's going to turn on like a t, like so. The problem is when we do the Laplace transform, if you remember your Laplace transform formulas for unit step function, this has to be of the same form as t minus 4, okay? And so what we're going to need to do, so this isn't going to quite work, but we're gonna make a small little notation here. The function t is actually equal to t minus 4 plus 4, right? Does t equal t minus 4 plus 4? Yes, it does. Okay. And now t minus 4 actually does look like t minus 4 that we need. So what I'm going to do is I'm going to actually write f of t is equal to t times the unit step function starting at t minus 4. And then I'm going to replace t with what I just put in these, what I just put right here. So now let's just step back a second. Is t equal to t? Yes. What's 4 minus 4 is 0. So this is true, right? And so wherever I have a t here, I'm going to just write t minus 4 plus 4. So it's going to be t minus 4 plus 4 times the unit step function starting at 4. Okay, so all I've done is replace t with t minus 4 plus 4. That's certainly true. And then I'm gonna expand this out. So I have t minus 4 times the unit step function starting at 4, and then plus 4 times the unit step function starting at 4. And what this is really doing is it's essentially saying, well, here's the t minus 4 function, right? Which looks like t, but starting at 4. And then if I add 4 to it, I will get what I originally started with. So this is t minus 4 starting at 4. And then if you add 4 to it, you will get the line we actually wanted, right? So that's all we're doing, and we do in fact have to do that because our Laplace transform formula for u requires it to be shifted the same way for the function as for the u, okay? So that's what we're going to do with that. Okay, so now we need to solve y prime plus 2y equals t minus 4 u t minus 4 plus 4 u t minus 4. Just like that. All right, so let's copy this, start a new page, and start solving. Okay, so what we're going to do is we're going to Laplace transform this entire differential equation. Okay, and of course, when you do that, you're going to Laplace each piece individually. And L of y prime is from our derivative formula. It's SL of y minus y of 0. And then L of 2y will just be 2L of y, like so. And then you might wonder, do we have an initial condition? I believe we do. Yeah, they gave us an initial condition. Y naught is 3. So we're going to be replacing that with 3 in a minute. So left-hand side, if we work it out, we're going to have s plus 2 L of y minus 3. That's the left-hand side. And of course, right there, that s plus 2, that's the characteristic equation that we're looking for from this. There's the s plus 2 characteristic equation, and that always comes out when you run things through the Laplace transform. Now let's look at right-hand side. So right-hand side, first we've got a shifted t function. So what we should get, we shifted it by 4, so we should be getting e to the minus 4s. That's coming from the shift, times the Laplace transform of the unshifted function, which is really t. Right? So this should be e to the minus 4s times, now what is the Laplace transform of t? I believe it's 1 over s squared, right? 1 factorial divided by s to the n plus 1. Well, it's t to the 1, so like so. And then the second one is we have 4. Now that's also been shifted. Of course, when you shift a constant, not much happens, but we're going to get e to the negative 4s times the Laplace transform of the 4 function, which should be, what? 1 over s is the constant function, so 4 over s, I guess. Okay, so then that comes down e to the minus 4s times 4 over s. Okay, so then L of y, what do we do to get that? We're going to add 3 to the other side. And then we will have to divide by this s plus 2. So we add the 3 to the other side, and then we divide everything by s plus 2. So we'll get 3 over s plus 2. This will become s squared s plus 2, and this will become s plus 2. And now we're in a position to work this out. But I think we're going to need some partial fractions for that, aren't we? So we're going to have 1 over s squared and s plus 2. We're going to need to split that. That should be what we should get. That should turn out to be something of the form a over s plus b over s squared plus c over s plus 2. And then we'll have e to the minus 4s. If we can fit this in here, this should end up with being some d over s plus e over s plus 2. Okay, so let's run those partial fractions through a minute here. So we'll need a blank space here. So let's do the first one. So we have 1 over s squared s plus 2. That's supposed to equal a over s plus b over s squared plus c over s plus 2. If we clear denominators, we're going to get, let's see, a s plus 2 plus b s plus 2 plus c s squared. All right, and we should be able to solve this using some of our standard tricks. For example, if we set s equal to 0, we're going to get 1 is equal to b times 2, because the a's and c's will cancel out when we set a equal to 0. So that tells you that b must have been 1/2. If we set s equal to negative 2, for example, then we'll get, let's see, that'll cancel, that will cancel, and we'll get c times 4. So I guess c must have equaled 1/4. And then I suppose we could note that there are no s squared terms on the left-hand side, but there are a s squared terms on the right-hand side and c s squared terms. So just looking at the two s squared terms here. But we know that c is 1/4. And so a, in order to get 0 s squareds on left-hand side, must have been negative 1/4 to get those to cancel. So a must have, in fact, been negative 1/4. Okay, so there's one of our partial fractions completed. The other one is what? 4 over ss plus 2 is supposed to equal d over s plus e over s plus 2. Clearing denominators, you're going to get 4 equals ds plus 2 plus es. And then what we can do is we can just set s equal to 0. And if we do that, we'll get 4 is equal to 2d. So d must have been 2. And if we set s equal to negative 2, then we will get, what? 4 is equal to e times negative 2. So e must have been, I guess, negative 2 as well. Okay. So now we've got the d and the e. And we can then essentially copy this whole business here. Start a new screen. Oh, we ran out of space there. We're going to need some, need another page or two, I suppose. Okay, so let's, we'll copy this whole business right here. We'll paste it down so we can start fresh. And then we're going to essentially just substitute in. I think all of this is multiplied by e to the negative 4s. So a was, let's see, what was a? Negative 1/4 over s. And b was 1/2, and c was 1/4. And d was 2, and e was negative 2. And we might as well combine terms since we've got a few. So we've got 2 minus 1/4 on the s, so that's what, 7/4 over s. And then on s squared, it looks like we just have the 1/2. And then on s plus 2, I guess we got negative 7/4. Because we have negative 2 plus 1/4. Okay. And that's equal to L of y. All right. So what was y then? So we take the inverse Laplace transform of the right-hand side. That should equal L of y. Or that should equal y of t. So what do we have here? We have 3 over s plus 2. That looks like 3e to the negative 2t by our standard Laplace transform formulas, right? And if we back up the truck 1 second here, what you're going to notice is that solves the homogeneous problem, in fact. Because at the beginning, the initial condition is 3. The homogeneous solution is e to the negative 2t. You can see it right from here. So 3e to the negative 2t solves that. And right-hand side forcing is 0 initially. So this right here is really just the solution to the homogeneous problem with 0 forcing term with initial condition 3. So that actually makes perfect sense. Everything else is what happens when you turn on right-hand side forcing at t equals 4, right? So all of this is the response to that forcing term. So how do we do that part? Well, what you're going to have here when you inverse this from the second translation theorem is you're going to have, well, this is telling you that it's shifting. So what does this come from and then shift it over by 4 units with a unit step function. So all of this should be unit step function t minus 4, right? Times everything, and everything's going to be shifted over. So 7/4 over s, that's a constant. That's coming from 1 over s, so that's just really the 7/4 function. And now that should be shifted, but when you shift a constant, nothing really happens. So it's just 7/4. But of course, it is turned on starting at 4 units. Then we're going to have this 1 over s squared function. So we're having 1/2, and then we have 1 over s squared. Well, that comes from a t, right? So the Laplace transform of t is 1 over s squared. But that t function should be shifted by 4 units. And then we're going to have negative 7/4, and then 1 over s plus 2, that would be e to the negative 2t, right? So that's coming from e to the negative 2t, but the t has to be shifted by 4 units from this. So we don't want e to the negative 2t, we want e to the negative 2t minus 4. And that as well will be turned on starting at t equals 4. So there's your solution. You basically have the homogeneous problem at the beginning, and then when the forcing term turns on at t equals 4, a new solution sparks out in response to that. You have a linear term in response to the linear term, and then this really is sort of another homogeneous solution that's basically balancing out the initial conditions, so you don't have a break in continuity or something like that.